Welcome to the IoT Dev Chat, a production of insight.tech. I'm Kenton Williston, the editor-in-chief of insight.tech and your host for today's podcast. Let's get into the conversation. In today's podcast, we'll be talking about machine vision with Johnny Chen from Logic Supply. Johnny, I'm really excited to talk to you today. Can you tell me a little bit about yourself, what your background is, and the kinds of machine vision technology you're working with?
Currently, I'm partnership and alliances is my current role. Previously, I was a solutions architect here at Logic Supply, working with customers, designing and both hardware and the software stack they will use. Logic Supply itself is very focused on machine vision applications.
And so one of the first things that I would like to know about the work you're doing there is what kinds of hardware you're using. You know, I think it's pretty obvious to everyone that machine vision is really hot right now, and that can be seen in the large number of players that are going after this market. You're seeing CPUs, GPUs, FPGAs, purpose-built vision processors. People are even rolling their own ASICs. So what kinds of hardware are you seeing as being the most important in this marketplace?
So in the industrial space, it's pretty unique because we have quite a few environmental challenges. So we use everything from CPUs, GPUs, and VPUs. Some customer applications they come from using external graphics, things like NVIDIA, but it really depends on the application. We've used almost every type of accelerators, including FPGAs and recently quite a bit of Movidius in different form factors and so forth.
So it sounds like from your perspective, there's an emerging trend towards the more specialized processors coming out on top. Would you agree with that?
Oh, definitely. It used to be everyone used GPUs. But I think with the trend of everything getting more specialized, especially at the edge, where the environment is not as friendly, where you really don't want a fan or you don't want something high-powered, that's where the advantage of things like a VPU comes in, something that's designed specific for vision.
And what about from the cost perspective? How does this new Movidius-style specialized hardware stack up?
Oh, it's definitely better than most customers think because you not only really are saving on the hardware side, where the real saving is cost of ownership and also reliability and power consumption. So the cost of ownership makes up those two things, reliability and power consumption. Not having a fan, having a lower power usage, all adds up very quickly.
The next thing that comes to mind for me is that the processor isn't everything, and so I'm wondering what the rest of the system looks like. And what I mean by that is, in a lot of applications, people have some existing equipment that they want to add vision capabilities to. So are they somehow retrofitting their existing compute hardware? Are they ripping and replacing and putting in something all new?
The most common approach I see is really, as they added these applications, they're building new compute, but they're adding it to old machines because these are large machines that will not be replaced because of the cost to replace them. But they're adding in the compute function with the cameras and so forth to add the vision capability into those machines.
And is that being done by, for example, adding a new box on top of what's already there, adding some software, doing some kind of add-in cards?
It really is. Usually it's providing a new box because adding in add-in cards to an existing system, you might not be able to take advantage of some of the newer platforms that's out today, especially in terms of compute power savings, as well as high reliability because of the lower power usage of the new systems.
That makes sense. That leads me to think about the level of customization that's happening there. If we're putting a new box on top of an existing system, is this something where you would want to build a highly customized solution? Is there some kind of a off-the-shelf approach that's typically preferable from a design time consideration?
I think from a time-to-market consideration, what we do quite a bit with is it's a customized solution. It's not a custom box per se. It's a customized solution. So we look at the customer's environment, we look at what their needs are and what their end goals are. We use quite a bit of off-the-shelf products, plus with some customization specifically for them. We do a lot of thermal design for their environment to make sure the machine can survive in that environment. We make sure there's enough compute and that is off the shelf. The compute portion is off the shelf. The cooling portions, a lot of times, is what we customize for the customer, depending on how much compute they need and what type of accelerators they're using. We have customers that use 1 to 2 Movidius chips, and we also have some applications that calls all the way up to 8 or more, really depending on the usage.
Wow. So, I don't think I've seen a lot of examples where you would have 8 vision processors in a system. What are some use cases where you would need that kind of performance?
Well, it depends on how much data you're processing. So some customers require real time. And then the nice thing about Movidius is you could actually split the workload to multiple chips, and they'll run in parallel. So a great example is automotive, for example. Not necessarily autonomous vehicles, but for, let's just say, mapping vehicles. Cars is driving outside, mapping the area, doing street shots. A lot of times they'll do real-time processing to collect and analyze the data right there. And then in real time, they'll even do things like blur out license plates, blur out faces. So this way, these are all privacy issues that they could do in real time right away.
There seems to be implicit in the conversation we've been having so far that what we're really talking about is doing machine vision via edge processing, which seems to clearly be where everything's heading. Are there instances where things are being done like in the data center or the cloud?
Well, that's an interesting question. What we're seeing is this. People are running models at the edge. So when you're at the edge, you're running the vision model, you're processing data. But at the same time, you're collecting new data. As you're collecting those new images and new data, you're sending it back to the server side. And what the server side is doing is incorporating that new data into the model and creating new models. And then these models get smarter and smarter as it gets more data. Then it pushes back out to the edge system to run the new model. The reason for the separation is a couple of things. One is you may have multiple edge devices all collecting data, and then you centralize the data to create the new model and push it all back out to those edge systems. Two is to create new models. There's a lot of compute there, and that is not necessarily what you want to put at the edge. At the edge is where you just want to run models.
But presumably the work you're doing at the edge can feed back into your model development to refresh and update
Correct.
And make your models better.
Correct. It works it's like a learning loop, right? So the edge is running the model, but also collecting new data. But it's sending that new data back to the central servers, collecting new data from all the edge machines, then crunching the data and creating a new model, and then push it back out to all the edge systems. So now you've created basically a learning loop. It will just get smarter and smarter over time. The longer you have the system, the better the model gets.
What kind of tools and frameworks and things of that nature are people using to actually do all of this work? I know there's a lot of things out there, TensorFlow, Caffe, et cetera. Do you see any one of these approaches gaining a lead over the others?
Well, personally, and what we've seen with customers more and more is there's a movement towards things like OpenVINO. One of the main advantages of OpenVINO is it allows you to basically write your code once. So what that means is I write my code once. I could actually assign it to different compute that's available to that system. So, for example, if I had an edge system, because of the extreme temperatures there, I could only have a CPU. I might not even be able to put a VPU inside because of that extreme temperature. I could use a CPU and the built-in GPU in the Intel silicon to actually run the model. That same code then could be repurposed for something in a nicer environment, industrial environment, where it's inside a factory, where I might have multiple Movidius chips on there. That same code will run on that. I do not need to recode, and I have more compute resources. So it's very adaptable. That gives you a big advantage because there's never going to be one machine fits all environments. This allows you to basically deploy your code on multiple different hardware.
So that sounds really appealing, the idea that not only could you write something once that could run on a single Movidius, multiple Movidius, but could also run on some combination of CPUs, GPUs, FPGAs. But of course, if I put myself in the developer's shoes, I think I could have some understandable skepticism about how well this is really going to work in practice. I guess the first question is, how do I know that this is really going to work at all? And closely followed behind that, am I going to get really suboptimal performance such that I kind of wish I had taken a more hardcore, highly optimized approach?
If you have a very clear vision what the end goal is, that code, once you put it through the translator, you assign it to the right compute or the right type of compute and how much real time you need it to be. It will work optimally for that compute. That's the whole idea of OpenVINO. The OpenVINO, the way it works is you basically assign what compute you want to use. And like I said, you could use a CPU core, you could use on the Movidius, you could use a GPU. A lot of times, because of the CPUs today, they're multi-core or they're up to 6 or 8, even more cores. A lot of times what our customers do is basically dedicate a core to a process, to run a particular process. That gives you almost real time. That's one way to do it. Like I said, because of the flexibility, it lets me use different hardware in combination with each other, and they work in parallel. That's the best part. So I could pick things to run the right way for what I needed to do.
So it sounds like what you're saying is, on one hand, you have this portability and this write once, run anywhere flexibility, but you still have, from an architectural standpoint, the ability to optimize your overall system by putting the right workloads in the right places so that you can get whatever performance you need.
Yeah, absolutely. I mean, a lot of people, for instance, use CUDA. CUDA is great because the GPU itself has a lot of little processors. The problem is, with the power of the GPU, these things run over 150 watts of power. Imagine if you were deploying this in real life. Here's a warehouse. You need 10, 20 of these systems. Using 150 watts plus doesn't make sense. Just the cost of utilities is going to be extremely high. Plus, you have fans. Now we're talking about reliability. Now imagine if you built specialized hardware using VPU, using the CPU, using the built-in GPU, and you cut that down to maybe 30 watts. You're looking at tremendous savings across the board, not just from a power consumption, but also reliability. This is why I think it's so important that we work with our clients to make sure we understand what is their end goal, what is the end application they're using it for, and then this way we can look at it and design for that.
So you end up with a more optimized solution, in other words. So this all sounds great, but I'm sure, as in any development project, there's always pitfalls and challenges that come up. And I'm curious what some of the biggest challenges you see when you talk to your customers.
A typical deployment or a typical someone that's just starting and they're using CUDA, it would be like an NVIDIA GPU and an Intel CPU. It's an interesting starting point, but in full production environment, it's unrealistic, especially for edge reliability because of two things. Again, power requirements and thermal requirements. So when you deploy an NVIDIA type system or a GPU type system, a dedicated GPU type systems, these GPUs take a lot of power. You're looking at 150 watts minimum on some of these GPUs. Imagine in a warehouse, you're deploying 10 of these. Now you're looking at, the amount of power you're using, first of all, is tremendously high. Second is the thermal requirements of your environment. GPUs are not designed really to be in those environments. Plus there's a fan that could fail, especially in an industrial environment where there's a lot of sand or there's a lot of dust in the air, or especially like carbon dust, which is conductive. These things are all things that would destroy the system. So from a reliability perspective and a thermal perspective, it makes a lot more sense to design something really designed for industrial, for that environment. For that same performance, we could do it down to a system that does about 30 watts of power, using Movidius, using the CPU, using the GPU. And this is where a tool like OpenVINO really comes in handy because I write the code once, it allows me to use it on all those compute components.
One of the things I'm also wondering about is the hacker approach to solving these problems. I imagine that there are shortcuts people try to take that end up getting them in trouble, right? Like maybe there's some kind of sneaky way they can deal with a power problem by just saying, well, just I won't cool it sufficiently and hope it'll last. Do you see people taking shortcuts like that you think they should avoid?
Yeah, I've seen some interesting shortcuts in my time here. An interesting one was particularly like the GPU, like cooling, for instance. There are people that will say, well, if it's in that type of environment, it's very dusty, I'll just do liquid cooling. Okay, interesting idea, but again, you're taking something that is a commercial approach into an industrial environment. Yes, liquid cooling does work. Liquid loops do work very well, but the cost and the maintenance of those are very high. And edge systems are typical systems that you really want to put it there and you won't forget about it. They just have to work all the time because any downtime costs you in productivity and so forth. So yes, we've had customers that use liquid cooling loops. It works until there's a leak or something happens, and then they lose a whole day of productivity. These are things that truly in an industrial environment, especially in a production environment, these are unacceptable. So we do have customers that come back to us and says, we tried this, it failed, and now we're ready to look at other solutions.
But I have to say that we've really been talking kind of general terms. Everything we've said so far, would you say it really applies across the board for pretty much all industrial use cases for machine vision? Yep. Or are there different approaches you need to consider for different specific applications?
Well, you definitely want to consider quite a few things. So an interesting example is autonomous robots. There's one great application that one of our customers use it for is for cleaning robots. So these are robots that basically roam through the building, clean the building. They'll even ride the elevator and go back to charge itself. 24/7, it avoids people, it avoids running into things. Now, when they started the project, they used a commercial off-the-shelf system. They ran a GPU. They did everything exactly the way how most people thought they should do it. They were running into a lot of failures because you have to realize, even though if you think about it, a cleaning robot, you would think a commercial system would be perfectly fine because it's just roaming the halls. Interesting enough, though, there are quite a few bumps it has to go over, like going into the elevator. These robots are pretty heavy, so the shock and vibe was actually making the systems fail. Everything from the fan to the GPU and so forth. So when we started working with them, we moved them to something that was fanless. We moved them from using a GPU to using Movidius. And so far, they have no failures. It's these little things that you don't think about. Over time, it wears out a machine. So once you go into a machine, once you move to a compute that is basically fanless, sealed, you don't have to worry about the environment, and it's designed for the environment that's in. You don't have those failures. So that was a really interesting, I would say, an application in which we worked with them to pick the right hardware and to put together the right custom system to fit that need.
That's a great example. So I'm wondering, as we look forward, it seems like today the transition is really from the standard graphics processor to a more specialized vision processor. And I'm wondering where you see things going next.
Well, I see things moving faster. I see more ASICs, like TPUs or VPUs, as an addition to the host processor. These are things that will work together. I see more integration, even these ASICs, into the host processors themselves. And I see integrate really into basically everything we do. Technology really has to become invisible in order to gain larger acceptance, in everyday things. So it has to integrate into our daily lives without us thinking about it. And it's already starting to happen, and especially with vision. There's no part of our daily life that will be touched by either machine learning or vision applications. Imagine your machines, your home appliance, your work machines. They're all smart enough eventually to be able to tell you when it needs to be maintained, what part needs to be maintained. Instead of running a standard maintenance schedule, it could actually run based on your usage model. How you use the machine, it'll know what part needs to be changed. These things will all become part of our daily lives.
Can't wait until my toaster is looking at me. Now, what about from the development methodologies? We've talked a lot about OpenVINO and how significant that is. Are there ways you see the software stack changing going forward?
In terms of development methodology, how are they changing? I think that the two biggest things, optimization, efficiency, it's the key to what I talked about technology becoming invisible. So we can't work in a bubble. Hardware has to work with software together to maximize that efficiency. This way, you keep enough overhead for future development, but you use enough for what you need today without wasting. And that's why I think it's so interesting, as we talk about like different SDKs and different types of tools you use, why I think flexibility of the tool is the most important thing. And OpenVINO gives you that. That's one of the tools that we see more and more coming up in terms of our customers asking for it, and we as a company recommend to people because it does help them. It does help them develop faster and get to market faster and have the proper hardware to match what their end needs are.
So before we go, I want to ask you the ultimate hard-to-answer question, which is if you had to give one piece of advice to a developer or an engineer who's just getting started on their first vision project, what would that be?
What I was saying earlier, it is keep it simple and have a clear vision. And look for SDKs that have flexibility and that's future-proof. What you hate to do is start on an SDK and basically it's for specific hardware and that hardware goes end of life. A great example I would say is Movidius itself when it first started, it had its own SDK. It worked well, but it was specific to Movidius. I don't think that the adoptability and also the interest really happened until OpenVINO happened. Because now it's not an SDK specific to one hardware. It's an SDK that will work on multiple hardware. So as a beginner or as someone just getting into this or starting your first project, your development time is going to be long. You don't want to start with an SDK that is too hardware specific because what's going to happen, it might happen, is by the time you develop the code, that hardware is no longer available or the SDK has changed so much for the new hardware that you'll have to start over.
Awesome. That totally makes sense to me. With that, we're out of time, so I just want to say thanks one more time, Johnny, for joining us. Really appreciated getting your insights.
Happy to be here.
Thanks so much for listening. As always, if you enjoyed today's podcast, please make sure to support us by subscribing and rating us on Apple Podcasts. And if you want to chat more about machine vision, make sure to tweet us at insight.tech. This has been the IoT Dev Chat Podcast. Join us next time for more conversations with industry leaders at the forefront of IoT design.